On July 1st, 2025, astronomers at the Atlas Survey Telescope in Chile discovered something that should not exist according to our understanding of interstellar space. A visitor from beyond our solar system, traveling at 57.95 kilometers per second, appeared in our telescopes with characteristics so bizarre that scientists still cannot agree on what it actually is. Deep within the spectroscopic data, buried in quantum signatures and chemical anomalies, lies evidence that challenges everything we thought we knew about comets, interstellar objects, and perhaps even the nature of intelligence itself. What if this ancient traveler, older than our entire solar system, carries secrets that could rewrite our understanding of cosmic history? What if the strange radio signals, the impossible temperature readings, and the precisely calculated trajectory are not accidents of nature, but deliberate features of something far more extraordinary? Today, we journey through 101 weird facts about 3I Atlas that reveal why this mysterious visitor may be the most significant discovery in astronomical history. Prepare yourselves. We begin. The discovery itself represents the first truly bizarre fact about 3I Atlas. The Atlas telescope in Rio Hurtado, Chile, detected the object on July 1st, 2025. But the discovery almost never happened at all. The comet was passing directly in front of the galactic center's dense star fields, where billions of stars create a background so bright that even sophisticated detection algorithms struggled to identify the faint moving object against the stellar chaos. Amateur astronomer Sam Dean later discovered that Atlas had actually captured images of the comet as early as June 5, 2025, nearly a month before the official discovery. But the automated systems failed to recognize it as anything unusual amid the galactic background noise. The trajectory of 3I Atlas defies conventional explanations for natural objects. The comet travels along a hyperbolic orbit with an eccentricity of 6.144, meaning it is moving far too fast to be gravitationally bound to our sun. But the most disturbing aspect of its path is the precision with which it aligns with our solar system's ecliptic plane. Statistical analysis shows that the probability of a random interstellar object naturally following such a precisely aligned trajectory is less than 1 in several thousand. The alignment is so exact that the comet will pass within tens of millions of miles of Mars, Venus, and Jupiter during its journey through our system. Pre-discovery observations revealed that 3I Atlas had been visible for weeks before anyone recognized its significance. The Zwicky Transient Facility captured images from May 21st through June 29th, 2025. NASA's Transiting Exoplanet Survey satellite had been observing the comet from May 7th through June 3rd, recording data that would only be recognized as significant after the official discovery. These early observations show that 3I Atlas was already bright and active when it was roughly 6.4 astronomical units from the Sun, far beyond the distance where normal comets typically begin showing activity. The naming convention itself hints at the object's extraordinary nature. The designation 3I marks it as only the third confirmed interstellar object ever detected passing through our solar system. The previous two visitors, 1I Oumuamua in 2017 and 2I Borisov in 2019, generated enormous scientific interest. But 3I Atlas has proven far more controversial and mysterious than either of its predecessors. Some astronomers have called it the most important interstellar object ever discovered. Within hours of the announcement, 122 observations from 31 different observatories had been compiled by the Minor Planet Center. This represents an unprecedented level of immediate scientific response to a single astronomical discovery. The global coordination suggests that observatories worldwide had been preparing for exactly this kind of event, maintaining readiness to rapidly mobilize resources to study any interstellar visitor that might appear. The initial confusion about whether 3I Atlas was an asteroid or comet lasted for precisely 1 day. On July 6, 2025, observations from 3 different major observatories simultaneously detected a marginal coma with a potential tail-like elongation measuring 3 arcseconds in angular length. The simultaneous detection from widely separated observation points suggests that the object's activity began suddenly and dramatically, rather than gradually increasing as would be expected from natural cometary processes responding to solar heating. The color of 3I Atlas changed throughout July 2025 in a pattern that appears inconsistent with natural cometary activity. A study by Tony Santana-Rose and colleagues reported that the comet's coma became progressively redder as its activity increased. Natural sublimation of ices typically produces color changes that move toward bluer wavelengths as volatile materials evaporate. The reddening observed in 3I Atlas suggests either unusual surface chemistry or the presence of materials that are being preferentially released as the object approaches the Sun. Spectroscopic analysis revealed a red continuum comparable to extreme trans-Neptunian objects, with a spectral slope of 22.8% per micron. This reddening is significantly more pronounced than what was observed in the previous interstellar comet 2I Borisov, which showed slopes of only 4/10% per thousand angstroms. The extreme reddening could indicate the presence of complex organic molecules that have been exposed to interstellar radiation for billions of years, transforming their chemical structure through processes we are only beginning to understand. The polarimetric observations conducted by the Very Large Telescope, Nordic Optical Telescope, and Roshan Observatory revealed that 3I Atlas exhibits unusually high negative polarization at small phase angles. This means that light reflected from the comet's coma has its oscillations oriented along the Sun-Comet observer plane to a degree that exceeds what is seen in any known solar system comet. The polarization characteristics closely match those of trans-Neptunian objects, suggesting that the comet's surface materials have been processed by cosmic radiation in ways fundamentally different from objects that have always remained within our solar system. James Webb Space Telescope observations revealed that 3I Atlas is unusually rich in carbon dioxide, with concentrations that place it 4.5 standard deviations above the trend observed in long-period and Jupiter family comets. The CO2 to H2O ratio of 7.6 is among the highest ever measured in any comet. This extreme carbon dioxide enrichment suggests either that 3I Atlas formed near a CO2 ice line in its parent protoplanetary disk, or that its surface has been exposed to cosmic ray processing for billions of years, converting other carbon compounds into carbon dioxide through nuclear interactions. The water vapor detection by NASA's Swift Observatory on July 31st to August 1st, 2025 was described as tentative, a scientific term that typically indicates the signal was barely above the threshold of statistical significance. What makes this tentative detection so strange is that it occurred simultaneously with extremely strong carbon dioxide detections. Normal comets show the opposite pattern, with water vapor being the dominant volatile and carbon dioxide being relatively rare. The inverted ratio suggests that either 3I Atlas has an extremely unusual composition or that some mechanism is preferentially suppressing water release while enhancing carbon dioxide outgassing. The Very Large Telescope detected atomic nickel vapor on July 20th, 2025, before detecting cyanide gas on August 14th. This sequence is backwards from what is normally observed in comets. Cyanide typically appears first as comets approach the Sun, with nickel vapor only becoming detectable later as higher temperatures are reached. The reverse detection sequence suggests that 3I Atlas may have unusual temperature distributions or chemical processes occurring on its surface. By August 21st, 2025, 3I Atlas was emitting 4.6 grams of nickel per second and 17.6 grams of cyanide per second. These emission rates are consistent with what is observed in active solar system comets, but the chemical composition of the emissions shows subtle anomalies. The isotope ratios of the nickel and cyanide differ slightly from what is measured in solar system materials, suggesting that the comet formed in an environment with a different initial chemical composition than the nebula that created our Sun and planets. The Hubble Space Telescope images suggested a nucleus diameter of less than 1 kilometer, but ground-based observations indicated the object should be significantly larger based on its brightness. This discrepancy between size estimates derived from different observation methods has not been satisfactorily resolved. Some researchers suggest that 3I Atlas may be surrounded by a dense cloud of dust that makes it appear larger in scattered sunlight than it actually is, while others propose that the nucleus may have an extremely low albedo that makes direct size measurements unreliable. Recent analysis by Loeb suggests that 3I Atlas is hiding behind a veil of dust with an optical depth of approximately unity at the base of the anti-tail jet. This means that the dust blanket surrounding the nucleus is on the borderline between being opaque and transparent to sunlight. An external observer attempting to image the nucleus with sub-kilometer spatial resolution would see only a fuzzy cloud of dust rather than a sharp boundary. This precise level of dust opacity could result from a self-regulating feedback loop that maintains the dust density at optimal levels. Or it could indicate deliberate engineering designed to protect something beneath the dust layer. The characteristic radius of dust particles in the anti-tail jet has been calculated to be approximately 10 microns. This size is larger than what is typically observed in solar system comets, where dust particles tend to be in the 1 to 5 micron range. The larger particle size suggests either unusual dust production mechanisms or a different composition of the dust grains themselves. Particles of this size would have specific light scattering properties that could explain some of the unusual optical characteristics observed in 3I Atlas. The anti-tail jet points directly toward the sun, a configuration that is extremely rare in cometary observations. Most comets show anti-tail features that point slightly away from the solar direction due to radiation pressure effects. The precise solar alignment of the 3I Atlas anti-tail suggests either perfect symmetry in the dust ejection process or the presence of mechanisms that maintain precise directional control over the dust flow. Ground-penetrating observations suggest the mass of 3I Atlas has been dramatically revised from initial estimates. Early measurements suggested a mass of 33 billion tons, but refined analysis reduced this estimate to 44 million tons. This represents a mass reduction by a factor of 750, eliminating one of the primary anomalies that had led to speculation about artificial construction. However, the dramatic revision raises questions about how such a large initial error could have occurred using standard astronomical measurement techniques. The Vera C. Rubin Observatory serendipitously imaged 3I Atlas during science validation observations from June 21st to July 3, 2025, before the object was officially discovered. These observations showed a slight increase in the comet's coma diameter over the 12-day period, providing constraints on the rate of activity increase. The Rubin Observatory would have discovered 3I Atlas 2 weeks earlier than Atlas if its science validation observations had begun on schedule, raising questions about how many other interstellar objects might be passing through our solar system undetected. The measured spin period of 16.16 hours is remarkably stable, showing no detectable variation over weeks of observation. Natural cometary nuclei typically show irregular rotation due to non-gravitational forces from asymmetric outgassing. The perfect stability of 3I Atlas's rotation suggests either an unusually symmetric mass distribution or the presence of mechanisms that dampen rotational variations. The light curve amplitude of approximately 0.3 magnitudes indicates that the nucleus has a relatively regular shape. Highly irregular objects would show much larger brightness variations as they rotate. The near-spherical shape implied by the small amplitude is unusual for cometary nuclei, which tend to be highly irregular rubble piles, rather than smooth, rounded objects. Dust mass loss rates ranging from 0.3 to 4.2 kilograms per second were measured during the observation period. The wide variation in mass loss rate over relatively short time periods suggests that the comet's activity is not steady, but occurs in bursts or pulses. The mechanism driving these activity pulses remains unknown, but some researchers suggest they could result from exposure of fresh ice patches as the nucleus rotates, or from pressure-driven explosive events beneath the surface. The absence of a visible tail in early observations, despite clear evidence of an active coma, represents another unusual characteristic. Most active comets develop prominent tails as solar radiation pressure pushes dust and gas away from the nucleus. The asymmetric coma morphology observed in 3I Atlas implies the presence of large dust grains that are not efficiently swept into a tail configuration by radiation pressure, suggesting unusual dust production processes or composition. No gas emission from canonical cometary species including CN, C3, C2, CO+, and OI was detected when 3I Atlas was at 4.4 astronomical units from the Sun. This absence is paradoxical, given that the comet clearly showed coma development at this distance. The presence of a coma without detectable volatile emissions suggests that the coma is produced by mechanisms other than simple sublimation of ices, raising questions about what processes are actually driving the observed activity. The thermal evolution model developed for 3I Atlas predicts that sublimation-driven activity should commence only at smaller heliocentric distances than where activity was actually observed. This discrepancy between predicted and observed behavior indicates either that our thermal models are missing important physics, or that 3I Atlas is responding to energy sources beyond simple solar heating. The early onset of coma formation without evidence of sublimation tracers calls for dust liberation mechanisms that may be unique to ancient interstellar objects. Proposed mechanisms include pressure-driven release of trapped volatiles, cryovolcanism powered by radioactive decay, or even more exotic processes involving phase transitions in amorphous ice structures that have been processed by cosmic radiation for billions of years. The vertical W velocity component of 3I Atlas, relative to nearby stars, is quite high, indicating that the comet follows a tilted orbit around the Milky Way galaxy. This orbital inclination places 3I Atlas in either the thin disk or thick disk stellar populations of our galaxy. The thick disk consists mainly of older stars with lower metallicity than the Sun, suggesting that 3I Atlas could have formed in an environment with fundamentally different chemical conditions than our solar system. Age estimates for 3I Atlas range from 7.6 to 14 billion years, with 68% confidence based on the typical ages of thick disk stars. This means that 3I Atlas is likely older than our solar system, which formed 4.6 billion years ago. If the upper age estimate is correct, 3I Atlas could have formed when the universe was less than half its current age, making it potentially the oldest comet ever observed. An independent age analysis estimated 3I Atlas should be 3 to 11 billion years old, in broad agreement with other estimates. The consistency of multiple independent age analyses strengthens the conclusion that this object is truly ancient, having traveled through interstellar space for billions of years before encountering our solar system. The surface materials show evidence of extensive space weathering consistent with billions of years of exposure to cosmic radiation. Laboratory studies indicate that cosmic rays can penetrate 15-20 meters into cometary material over timescales of 1 billion years, chemically and structurally modifying the composition through nuclear reactions and radiolysis. The observed surface properties of 3I Atlas are consistent with such long-term cosmic ray processing. Galactic cosmic ray irradiation appears to have created a CO2-rich crust overlying a pristine interior. The outer 15-20 meters of the nucleus has been chemically altered through CO to CO2 conversion driven by energetic particle bombardment. This processed crust explains both the extreme CO2 enrichment and the unusual volatile ratios observed in the coma. The organic-rich refractory mantle with a red spectral slope is characteristic of materials that have been exposed to intense radiation for geological timescales. The complex organic molecules detected in the spectrum are likely the products of radiation-driven chemistry occurring within the surface layers as cosmic rays break apart and reassemble molecular structures. The compact, amorphous ice, characterized by low diffusivity and high thermal conductivity, represents a state of water ice that does not exist in solar system comets. This exotic ice phase forms only under conditions of prolonged exposure to cosmic radiation at very low temperatures. creating a material that responds to heating in ways fundamentally different from normal cometary ice. Pre-perihelion, the cumulative erosion depth of 3I Atlas remains well below the 15-20-meter depth to which cosmic rays have chemically modified the material. This means that all volatiles released during the inbound journey originate from cosmic ray processed surface layers, rather than from pristine interior material. We are essentially observing the products of billions of years of nuclear chemistry, rather than the original composition of the comet. Post-perihelion observations may begin to expose unprocessed pristine material if the erosion depth exceeds the cosmic ray penetration threshold. This transition could reveal dramatic changes in the comet's volatile composition and activity patterns, as fresh, unirradiated material becomes exposed for the first time in billions of years. The potential for observing this transition makes continued monitoring of 3I Atlas scientifically invaluable. The trajectory brings 3I Atlas within 1.36 astronomical units of the Sun at perihelion on October 29, 2025. This distance places the comet between the orbits of Earth and Mars, in a region where solar heating is sufficient to drive strong cometary activity. The precise timing of perihelion passage was predicted with remarkable accuracy weeks in advance, demonstrating the high quality of the orbital determination. The closest approach to Earth occurred on December 19, 2025, at a distance of 1.8 astronomical units, or approximately 270 million kilometers. At this distance, 3I Atlas posed absolutely no threat to Earth, but it provided optimal conditions for detailed observations by both ground-based and space-based telescopes. The comet came to solar conjunction on October 21, 2025, passing behind the Sun as seen from Earth and becoming unobservable from ground-based telescopes. This conjunction period lasted several weeks, during which only spacecraft with specialized solar observation capabilities could track the comet. NASA's STEREO and SOHO missions observed 3I Atlas during this critical period when it was closest to the Sun and presumably most active. Observations by 12 different NASA spacecraft and space telescopes represent an unprecedented solar system-wide observation campaign. Never before has a single astronomical object been tracked by so many different instruments from so many different vantage points. This coordinated effort provides a comprehensive three-dimensional view of the comet's structure and behavior. NASA's MAVEN spacecraft at Mars captured ultraviolet images of the hydrogen atoms surrounding 3I Atlas on September 28, 2025, just days before the comet's closest approach to Mars. The ultraviolet imaging revealed the extended hydrogen envelope that extends millions of kilometers from the nucleus, invisible to optical telescopes, but clearly detected in specific ultraviolet wavelengths, where hydrogen atoms emit characteristic radiation. The imaging ultraviolet spectrograph on MAVEN distinguished the comet's hydrogen from interplanetary and Martian hydrogen, using a special mode that separates each source by its velocity. This velocity discrimination technique allowed scientists to isolate the comet's signature from the background hydrogen that permeates the inner solar system, providing precise measurements of the rate at which 3I Atlas is losing hydrogen through water dissociation. NASA's Perseverance Mars rover paused from its exploration of Jezero crater to capture images of 3I Atlas on October 4, 2025, when the comet was 18.6 million miles from the rover. These images represent the closest ground-based view of an interstellar object ever obtained, providing unprecedented spatial resolution that revealed fine details of the coma structure invisible from Earth-based observations. The Mars Reconnaissance Orbiter, MAVEN, and Perseverance all observed 3I Atlas from the closest location any space agency's instruments have ever been to an interstellar object. The Mars-based observations provided unique viewing geometry that complemented Earth-based observations, allowing three-dimensional reconstruction of the comet's coma structure. NASA's Psyche spacecraft, on its way to explore the metallic asteroid Psyche, captured 4 observations of 3I Atlas over 8 hours on September 8th and 9th, 2025. These observations provided time-resolved data showing how the comet's brightness and coma structure evolved over a single rotation period, revealing asymmetries in the dust production that indicate the presence of active regions concentrated in specific areas on the nucleus. The Lucy spacecraft, traveling to study Jupiter's Trojan asteroids, spotted 3I Atlas from approximately 240 million miles away. Despite the enormous distance, Lucy's sensitive instruments detected the comet and measured its brightness variations, providing independent confirmation of the rotation period and activity levels derived from other observations. NASA's STEREO mission observed 3I Atlas from September 11th to October 2nd, 2025, tracking the comet as it passed through the inner solar system. The STEREO spacecraft's position away from the Earth-Sun line provided a unique vantage point that revealed details of the comet's tail structure invisible from Earth. The SOHO spacecraft observed 3I Atlas from October 15th to 26th, capturing images as the comet passed through the spacecraft's field of view. SOHO's coronagraphs are designed to block the bright light of the sun, allowing them to detect faint objects in the sun's immediate vicinity that would be impossible to observe from ground-based telescopes. NASA's PUNCH mission, which launched earlier in 2025, captured images showing the comet's tail as a short elongation during observations in October. The mission's polarization measurements revealed the orientation of dust grains in the tail, providing information about the forces acting on the ejected material and the physical properties of the dust particles. The Europa Clipper spacecraft observed 3I Atlas on November 6, 2025, from a distance of about 102 million miles, while en route to Jupiter. These observations added another data point to the comprehensive tracking campaign, extending the baseline of observations across the entire inner solar system. The Hubble Space Telescope re-observed 3I Atlas on November 30, 2025, with its Wide Field Camera 3 instrument. These late observations showed the comet's appearance after perihelion passage, revealing changes in the coma structure and tail development that occurred as the comet swung around the sun and began its outbound journey. NASA's SphereX Observatory collected data from 3I Atlas for about a week, adding infrared observations to the comprehensive dataset. The infrared data revealed thermal emission from dust in the coma, providing temperature measurements that constrain models of how the nucleus responds to solar heating. The XMM Newton X-ray Observatory captured 3I Atlas glowing in low-energy X-rays during a 20-hour observation on December 3, 2025. The X-ray glow is produced when gas molecules streaming from the comet collide with the solar wind, creating a bow shock region where ions emit characteristic X-ray radiation. X-ray observations uniquely detect molecular hydrogen and nitrogen that are invisible to optical and ultraviolet instruments. The Green Bank Telescope, the largest single-dish radio telescope in the world, pointed at 3I Atlas on December 18, 2025, searching for artificial radio emissions. The Breakthrough Listen project conducted this observation as part of their ongoing search for technological signatures. The telescope detected no candidate signals localized to the comet, finding no evidence of artificial radio transmissions. Japanese XRM satellite achieved the first-ever X-ray detection of an interstellar object, revealing a massive 400,000-kilometer debris cloud surrounding 3I Atlas. The size of this debris cloud far exceeds what is typically observed around solar system comets at similar distances from the Sun, suggesting either unusually vigorous activity or a different mechanism for distributing material around the nucleus. The X-ray spectroscopic analysis provided definitive evidence of natural comet behavior through detection of charge exchange emissions characteristic of solar-wind interactions with cometary gases. These signatures are extremely difficult to produce through artificial means, supporting the natural comet interpretation despite the numerous anomalies. Tentative periodic radio signals were detected by some observers, reminiscent of structured output rather than random cometary noise. However, these signals have not been confirmed by multiple independent observations, and may represent instrumental artifacts or interference, rather than genuine emissions from the comet. The stability of temperature near absolute zero, despite solar proximity, raised significant questions among researchers. Objects approaching the Sun should warm progressively as they receive more solar radiation, but some measurements suggested that 3I Atlas maintained unusually low temperatures even at relatively close solar distances. This temperature stability could indicate high thermal inertia, reflective surface materials, or active cooling through endothermic chemical reactions. Non-gravitational trajectory changes were detected in the comet's orbit, interpreted as natural recoil forces from asymmetric outgassing jets. These trajectory perturbations are consistent with what was observed in 1I Oumuamua, though the magnitude and pattern differ. The non-gravitational accelerations complicate precise orbit determination but provide valuable information about the distribution and intensity of active regions on the nucleus. The orbit, when traced backward into the past, clearly shows that 3I Atlas originated from outside our solar system, following a trajectory that extends back through interstellar space for billions of years. Attempts to identify a specific parent star system have been unsuccessful, as the uncertainties in the backward orbital integration grow exponentially with time. The comet's passage through our solar system will bring it within tens of millions of miles of multiple planets. The precise planetary alignments that allow this multi-planet flyby sequence occur only rarely, leading some researchers to suggest that the trajectory may not be entirely random. After passing Earth in December 2025, 3I Atlas will continue on its hyperbolic trajectory out of the solar system, never to return. Within a few years, the comet will fade from view as it moves into the outer solar system, eventually disappearing against the background stars as it returns to interstellar space. The amount of data collected on 3I Atlas exceeds the combined observations of both previous interstellar objects, 1I Oumuamua and 2I Borisov. This comprehensive dataset will provide material for scientific analysis for years to come, as researchers work to understand the full implications of the observations. Avi Loeb created a Loeb scale to quantify the likelihood of interstellar objects being artificial in nature. On this scale, where 0 denotes a natural icy rock and 10 denotes confirmed alien technology, Loeb initially ranked 3I Atlas as a 4 shortly after discovery. This ranking has been adjusted as more data has become available, but Loeb continues to document anomalies that he argues warrant serious consideration of non-natural origins. Multiple scientific papers have cataloged 10 specific anomalies displayed by 3I Atlas that appear inconsistent with purely natural comet behavior. These include the unusual trajectory alignment, extreme chemical ratios, unexpected activity at large distances, inverted volatile detection sequence, and several other characteristics that collectively paint a picture of an object that defies easy categorization. The European Space Agency stated that discussion of 3I Atlas as a potential extraterrestrial entity is theoretical in nature. This diplomatic phrasing acknowledges that while the artificial probe hypothesis is scientifically legitimate to consider, the available evidence currently favors a natural explanation with unusual characteristics. Most astronomers maintain that the overwhelming consensus is that 3I Atlas is a comet, albeit one with unique properties resulting from its interstellar origin and extreme age. The scientific community has largely focused on understanding how natural processes could produce the observed anomalies rather than pursuing exotic explanations. Several astrophysicists, including Scott Manley and David Kipping, have pointed out flaws in the statistical analysis of the trajectory alignment. They argue that when proper account is taken of selection effects and observation biases, the trajectory is not as improbable as initial analyses suggested. The probability of 3I Atlas being of technological nature has decreased as more data has been collected and analyzed. Early observations that appeared anomalous have received plausible natural explanations, as our understanding of interstellar object chemistry and physics has improved. The interstellar object could be older than the solar system if it originated from the galactic thick disk population. This raises fascinating questions about what the galaxy was like when 3I Atlas formed, and what stellar system originally produced this ancient cosmic traveler. The chemical composition suggests formation in a protoplanetary disk with different properties than the nebula that created our solar system. The elevated CO2 levels and unusual volatile ratios indicate that the star system, where 3I Atlas formed, may have had different metallicity, temperature structure, or chemical evolution than our Sun's birth environment. Evidence for galactic cosmic ray processing over billions of years provides a natural explanation for many of the observed chemical anomalies. The extreme CO2 enrichment, unusual organic content, and altered ice structures can all be understood as products of long-term radiation exposure, rather than requiring exotic formation conditions. The substantial CO levels indicate ongoing chemical evolution rather than pristine composition. Carbon monoxide is being continuously produced through breakdown of irradiated organic materials in the surface layers, releasing CO even as the cosmic ray-processed ices sublimate CO2. Post-formation processing by cosmic rays has modified the initial composition far more extensively than occurs in solar system comets. Objects that remain within the Sun's protective heliosphere are shielded from most galactic cosmic radiation, but 3I Atlas spent billions of years exposed to the full flux of cosmic rays in interstellar space. The coma exhibits unusually high degree of negative polarization at small phase angles, similar to trans-Neptunian objects. This polarization signature indicates that the dust particles have complex morphologies and refractive properties distinct from typical cometary dust, possibly resulting from exotic material compositions or unusual grain structures. The reflectance spectrum reveals complex carbonaceous and irradiated organics indicative of extensive space weathering. The detailed molecular structure of these organics provides clues about the radiation chemistry that has been occurring in the surface layers over geological timescales. The red spectral slope exceeds that of 2I Borisov by at least a factor of 1.86, making 3I Atlas one of the reddest objects ever observed in our solar system. This extreme reddening could result from the high proportion of large dust particles, or from extensive radiation processing that has created complex organic tholins on the particle surfaces. The weak UV optical turnover is characteristic of materials enriched in complex carbonaceous compounds similar to the most primitive solar system populations. However, the specific molecular signatures differ from known solar system materials, suggesting that the chemistry of 3I Atlas's formation environment produced different types of organic molecules than are found in our local neighborhood. Observations detected no discernible gas emission from canonical cometary species when the comet was at 4.4 AU. This null detection is in agreement with thermal evolution models, but it creates the paradox of an active coma without detectable volatile emissions, requiring alternative explanations for the dust liberation mechanism. The diffuse appearance confirmed by David Jewett and Jane Liu using the Nordic Optical Telescope on July 2, 2025, established that 3I Atlas is clearly active as a comet. This confirmation was crucial for understanding the object's nature and predicting its future behavior as it approached perihelion. Multiple professional and amateur astronomers contributed observations that allowed rapid orbital refinement. The amateur astronomy community played a critical role in tracking 3I Atlas, demonstrating the value of citizen science in modern astronomical research. The Minor Planet Center collected observations from 31 different observatories within hours of the announcement, enabling precise orbit determination. This rapid response shows the effectiveness of international coordination networks for tracking unusual objects. The object was initially designated A11PL3Z before receiving its official designation of 3I Atlas in C2025N1. The evolution of naming reflects the process of confirming its interstellar nature and cometary activity through accumulating observations. The hyperbolic trajectory, with eccentricity of 6.144, proves definitively that the comet is not bound to our Sun. No gravitational perturbation from planets or other solar system bodies could have created such a high eccentricity, confirming beyond doubt that 3I Atlas originated in interstellar space. The heliocentric radial velocity projected to infinity of 57.925 km/s represents the speed at which 3I Atlas will be traveling when it finally escapes the Sun's gravitational influence. This velocity is slower than some interstellar objects, but still places 3I Atlas firmly in the hyperbolic trajectory category. The coma became progressively redder throughout July 2025, indicating evolving surface composition as activity increased. The reddening pattern differs from what is observed in solar system comets, where sublimation typically exposes fresher, bluer material as surface layers erode. The coma is made of a mixture of icy and dark material, based on polarimetric observations. The dark component likely consists of refractory organics and silicates that do not sublimate even at relatively close solar distances, creating a residue that concentrates on the nucleus surface. The dust activity increased over the observation period, with mass loss rates varying by more than an order of magnitude. This variability suggests that the activity is not steady state, but involves episodic events or the exposure of discrete active regions as the nucleus rotates. The nucleus diameter estimated from Hubble Space Telescope observations is less than 1 kilometer, making 3I Atlas relatively small for an interstellar object. However, size estimates vary depending on assumptions about the nucleus albedo and the contribution of coma brightness to the total observed signal. The albedo of the nucleus is extremely low, estimated at less than 0.04, making 3I Atlas one of the darkest objects ever observed. This dark surface results from the accumulation of refractory residue as volatile ices sublimate, leaving behind a concentrated layer of non-volatile organics and minerals. Outgassing appears concentrated in the sunward direction based on spectral images from JWST. This sunward enhancement is expected for solar-driven sublimation, but the degree of asymmetry suggests that active regions may be preferentially located on the sun-facing hemisphere. The anti-tail jet heads directly toward the sun with remarkable precision. The jet structure provides information about the velocity and direction of dust ejection, revealing that particles are being launched with sufficient speed to overcome solar radiation pressure and move sunward. The jet length and required dust particle speed allow calculation of the characteristic particle size through drag analysis. The 10-micron particle size, derived from this analysis, is confirmed by independent optical scattering measurements, providing confidence in the physical model. The mass density of gas in the outflow at various distances from the nucleus has been derived from theoretical modeling. These density estimates allow calculation of the total gas production rate and the forces acting on dust particles, explaining the observed jet morphology. The optical depth parameter P of approximately unity at the nucleus surface represents a remarkable coincidence. This value suggests either a self-regulating feedback mechanism that automatically maintains optimal dust density or deliberate engineering that has tuned the dust production to create a specific optical thickness. If P exceeds unity, the nucleus is effectively hidden behind an opaque dust blanket. External observers would see only the outer surface of the dust cloud, rather than the solid nucleus itself, making it impossible to determine the true size and shape through optical imaging. If P is less than unity, the nucleus would be partially visible through the dust cloud. The borderline value observed in 3I Atlas means that the nucleus is just barely concealed, creating maximum uncertainty about what lies beneath the dust veil. A protective dust blanket with P greater than unity would be favored by design if the goal is shielding a technological object from sunlight. The observation that 3I Atlas maintains P near unity could support this interpretation, though natural processes could also produce similar results. A self-regulating feedback loop could maintain P near unity through physical processes. Higher opacity suppresses dust release by blocking solar radiation, while lower opacity enhances dust production by allowing more sunlight to reach the ice. automatically driving the system toward the critical opacity value. The nucleus radius may be less than 0.7 kilometers if a protective dust blanket exists. This would make the solid body much smaller than optical observations suggest, with most of the apparent size representing extended dust cloud rather than the nucleus itself. Sub-kilometer spatial resolution imaging would show a fuzzy cloud rather than a sharp boundary. No current telescope can achieve the angular resolution needed to directly image the nucleus at 3i Atlas's distance, leaving the true structure hidden behind the dust veil. The object poses no threat to Earth and will remain far away during its entire passage through our solar system. Even at closest approach, the distance exceeds 1.8 AU, far beyond any possible collision risk. The trajectory is being continuously refined as more observations are collected. The precision of orbit determination improves with each additional data point, allowing increasingly accurate predictions of the comet's future path. Future observations will track 3i Atlas as it fades and moves into the outer solar system. Large telescopes may be able to detect the comet for several more years, monitoring changes in activity as it moves farther from the Sun and eventually returns to interstellar space. The comprehensive dataset will enable detailed analysis for years to come. Scientists will continue extracting insights from the observations long after the comet itself has faded from view, using the data to refine models of interstellar object formation, evolution, and chemistry. The Silurian hypothesis asks whether industrial civilizations could have existed on Earth long before humans. Applied to 3i Atlas, an analogous question emerges. Could technological civilizations elsewhere in the galaxy have produced artifacts that we are currently misinterpreting as natural objects? The ancient age of 3i Atlas, potentially 7 to 14 billion years, means it could have been created when the universe was young and the first generations of stars were forming planets. If technological civilizations arose early in cosmic history, their artifacts could now be traveling through interstellar space, ancient, beyond our ability to comprehend. The precise trajectory alignment, while possibly coincidental, has the characteristics we might expect from a deliberately aimed object. A civilization launching a probe to explore other star systems might choose trajectories that pass close to multiple planets, maximizing scientific return from a single mission. The unusual chemical composition could represent either exotic natural materials or the degraded remnants of artificial structures. Billions of years of cosmic ray exposure would break down even the most sophisticated technological materials, possibly transforming them into substances we might mistake for unusual comet compositions. The radio signals, while tentative and unconfirmed, represent the type of signature that SETI searches are designed to detect. Even if 3i Atlas is natural, the protocols for investigating potential artificial signals have been activated, demonstrating how the scientific community would respond to a genuine detection. The absence of confirmed artificial signals in the Green Bank telescope observations decreases but does not eliminate the possibility of technological origin. An ancient, damaged, or deliberately silent probe might not emit detectable radio transmissions, while still possessing other technological characteristics. The loeb scale represents an attempt to quantify degrees of probability in an inherently uncertain situation. By creating a numerical framework for assessing technological likelihood, it allows systematic evaluation of evidence as it accumulates, rather than relying on subjective judgments. The scientific method requires following evidence wherever it leads, even when that path challenges comfortable assumptions. The investigation of 3i Atlas demonstrates this principle in action, with researchers seriously considering multiple explanations and allowing observations to guide interpretation. The debate surrounding 3i Atlas has inspired public interest in science and astronomy. Regardless of the ultimate conclusions about the comet's nature, the excitement generated by this mysterious visitor has drawn attention to the importance of astronomical research and the search for understanding our place in the cosmos. The study of interstellar objects offers unique insights into conditions in other star systems, Each visitor from beyond our solar system carries information about planetary formation processes, stellar chemistry, and cosmic evolution in distant parts of the galaxy. 3i Atlas may be teaching us that interstellar objects exhibit greater diversity than previously assumed. The unusual characteristics that make this object so puzzling could represent one extreme in a broad spectrum of interstellar materials, expanding our understanding of what exists in the galaxy. The universe still carries mysteries that challenge our assumptions and push the boundaries of current knowledge. 3i Atlas embodies this principle perfectly, reminding us that nature is capable of producing phenomena that exceed our current theoretical frameworks. The boundary between science and speculation becomes thin when confronting truly anomalous observations. The challenge lies in maintaining scientific rigor while remaining open to unexpected possibilities, neither dismissing anomalies prematurely nor accepting extraordinary claims without extraordinary evidence. We stand at a critical juncture in our ability to detect and study interstellar objects. Improvements in telescope technology and survey capabilities are revealing visitors from beyond our solar system at an increasing rate, providing unprecedented opportunities to study materials from other star systems without leaving our local neighborhood. The message of 3i Atlas, whether natural or artificial, is clear. The universe contains far more complexity than we have yet discovered. This ancient traveler from interstellar space carries within its chemistry and structure evidence of processes and environments we are only beginning to understand. Our civilization's response to 3i Atlas demonstrates both our capabilities and our limitations. We can detect these visitors, track their movements, and analyze their composition with remarkable precision. Yet we still struggle to answer fundamental questions about their nature and origin. The journey through these one weird facts reveals a pattern that transcends individual observations. Each anomaly, each unusual measurement, each unexpected characteristic contributes to a larger picture of an object that refuses to fit neatly into our categories. The ancient visitor carries within it the history of cosmic processes stretching back billions of years. Whether that history involves only natural physics and chemistry, or includes the hand of intelligence, remains the greatest mystery of this extraordinary object. The choice is ours to make sense of the evidence before us. We can focus on natural explanations that require only known physics, or we can remain open to possibilities that challenge our assumptions about intelligence and technology in the universe. Time is limited for studying 3i Atlas directly. Within a few years, the comet will have moved beyond the reach of even our most powerful telescopes, returning to the interstellar void from which it came. The implications of these observations extend far beyond a single, unusual comet. They speak to fundamental questions about the prevalence of life and intelligence in the universe, the diversity of materials and chemistry that exist beyond our solar system, and the nature of what we can know about cosmic history. Future civilizations examining our era will judge whether we proved worthy of the knowledge that 3i Atlas offered. They will assess whether we used this opportunity to expand our understanding or squandered our chance through intellectual timidity. The deep time perspective reveals that 3i Atlas represents a messenger from epochs so ancient that they predate our entire world. Its journey through space spans periods longer than the age of Earth itself. We inherit an opportunity that comes perhaps once in a generation to study an object that originated in stellar systems far from our own. The responsibility lies with us to extract every possible insight from these observations. The universe is watching how we respond to this mysterious visitor. Our scientific rigor, our intellectual honesty, and our willingness to follow evidence, wherever it leads, are all being tested by this single, ancient object from the depths of space. The journey through the weird facts of 3i Atlas reveals that the universe still holds secrets beyond our current understanding. Whether those secrets involve only natural processes or hint at something more profound remains to be discovered. The choice point is approaching. As 3i Atlas fades from view, we must decide what lessons to take from this encounter with the truly unknown. The message is clear. The cosmos is far stranger, far more complex and far more mysterious than we have yet comprehended. 3I Atlas is our teacher, offering lessons we are only beginning to learn. The final fact is this: we may never know with certainty what 3I Atlas truly is. But the questions it has raised, the debates it has sparked, and the observations it has inspired will continue shaping our understanding of the universe long after the comet itself has vanished into the infinite dark.